Hi, my name is Astawu. I'm a student in the Nav Lab headed by Professor Grace Gao at Stanford University, and today I will be presenting on bounding GPS-based positioning and navigation uncertainty for autonomous drifting via reachability. Since I've mentioned autonomous drifting in the title of this work, let me start off by showing a demonstration of autonomous drifting. This demonstration was completed by our collaborators in the Stanford Dynamic Design Lab. The car is fully autonomous with a GPS receiver and IMU on board. While drifting is often considered only in the context of motorsports, it also lends itself to lessons in the larger context of autonomous driving. Our overall goal is to ensure safety of autonomous vehicles under extreme dynamics. One such example of extreme dynamics is autonomous drifting. Drifting is a maneuver with extreme dynamics characterized by high side slip angles and slip of the rear tires. Sometimes it can accidentally occur in hazardous conditions, such as on wet or icy roads. Thus, studying autonomous drifting provides insights into safe navigation of autonomous vehicles in hazardous conditions that may compromise driver safety. This then leads us to our motivating question. In these safety-critical scenarios, where we might want to provide safety guarantees, from a navigation perspective, can we infer the worst-case estimation performance of our system under uncertainty? Now, what are the sources of uncertainty that we may be concerned about in autonomous drifting? To illustrate the sources of uncertainty that may arise in drifting, let us revisit our drifting demonstration. The car is equipped with a GPS receiver and IMU, which are subject to measurement uncertainties. Some common factors that contribute to measurement uncertainty are listed here. First, measurements are subject to noise from some unknown underlying probabilistic distribution. Second, we may experience communication losses. For example, the GPS receiver may lose connection with a base station, thereby causing losses in the base station corrections. And finally, the measurements may be subject to outliers or biases from environmental factors. In addition to measurement uncertainty, we're also concerned about motion uncertainty. As with all dynamic systems, drifting is subject to propagation noises. We also might be concerned with the modeling of the friction parameter between the tire and the road, as changes in this parameter changes how we believe the car will move. And finally, there may be controller input noises. For this work, we focus on measurement uncertainty, specifically in the uncertainty in double difference GPS pseudo-range measurements. Now that I have framed the source of uncertainty we are concerned about, in safety-critical applications, it may not be enough to characterize the uncertainty. Rather, to provide safety guarantees, we would want to be able to bound the estimation uncertainty to inform the worst-case performance. And to do so, we use reachability analysis. To illustrate why, I'll highlight a few key differences between classic filtering techniques, such as Kalman filters, and reachability-based methods. In traditional filtering, we receive a measurement, and we assume that the measurement noise follows a very specific noise distribution. Then, given the assumption on the noise distribution, the filter produces a current point estimate of the state and an estimation error ellipse derived from the covariance matrix. In this way, these classic filtering techniques provide likelihoods as measures of the estimation uncertainty, but they cannot bound the estimation uncertainty, which is less useful for worst-case considerations. On the other hand, in reachability-based estimation methods, given a measurement, and assuming that the measurement noise is bounded, without any additional assumption on the distribution, The method generates an estimated state set that is also consistent with the measurements and bounded measurement noise. Leveraging set membership properties, reachability analysis provides guarantees that your true state must reside within the estimated state set, thus also bounding the estimation uncertainty. As such, we investigate reachability-based methods for our worst-case considerations. Several different methods for reachability-based estimation exist in the prior literature. These approaches are often categorized by how measurements are integrated with system dynamics. Two such categories are set propagation observers and strip-based observers. Set propagation observers are loosely speaking the set-based parallel to classic filtering techniques. For measurement assimilation, as illustrated here, the measurement residuals are weighted according to an observer gain, and then the corrections are added to the state set. In contrast, strip-based observers generally assimilate measurements by performing intersections between the state set and a measurement set, as illustrated here. Then, while set propagation observers are generally found to be more computationally efficient than strip-based observers, strip-based observers were found to often provide tighter guarantees, meaning smaller bounds, than set propagation observers. Furthermore, while set propagation observers have been demonstrated on bounding uncertainty for estimation with GPS pseudo-range, to the best of our knowledge, no prior work has applied a strip-based observer for bounding estimation uncertainty with GPS measurements and drift dynamics. For this reason, we focus on strip-based observers in this work. Our contributions are as follows. We apply a strip-based estimation framework on nonlinear drift dynamics with double difference GPS pseudo-range measurements. Then we demonstrate the framework's ability to bound estimation uncertainty for different noise distributions and amplitudes through sensitivity testing. Finally, we validate the reachability-based estimation framework using real-world drifting data. The remainder of the presentation is split into three sections. First, I will discuss the strip-based estimation framework, starting with an introduction to our chosen set representation. Then I will give an overview of the framework and provide more insights into the dynamics and measurement model. The second section will be on our framework validation in both simulation and with real-world data. We use simulation as a way to validate our framework in a more controlled environment and to allow us to experiment with a variety of noise profiles. Then we validate in real world as a first step to bridging the sim to real gap. In the final section, I will conclude the presentation. Let me start by giving some background into our chosen set representation, zonotopes. We can build the definition of a zonotope by first considering a unitary box, which is shown in 2D here. Unitary means that the upper and lower bounds are 1 and -1. A zonotope can then be constructed from the unitary box through an affine transformation where C is the center of the zonotope and G is the generator matrix. Now, why do we want to use zonotopes? When dealing with set-based estimation, there are three common operations that we encounter, specifically Minkowski sum, linear map, and intersection, which are defined here. In the context of set-based estimation, we choose a zonotopic representation because zonotopes are closed under Minkowski sum and linear maps, meaning that for these operations, they produce less conservative bounds than other set representations. Now that I've defined our set representation, I'll give an overview of the zonotopic estimation framework. The key assumptions of this framework are that motion and sensing uncertainties are bounded. Structurally, the framework is very similar to classic filtering techniques with a propagation and measurement update step. So we start with a state set at time t. Then we propagate the set forward in a manner that is consistent with the dynamics and bounded process noise, and this produces the new set shown in blue. This is the prediction step. Then we receive double difference pseudo-range measurements, and using the received measurements and measurement noise bounds, we construct a consistent state set. Then we assimilate the measurements by intersecting the prediction set and the measurement set. This is the measurement update. Finally, we minimize the volume of the zonotope to produce a final state estimate. Now I'll give a little more insight into the propagation step with drift dynamics. We use a single track model with some simplifications. The car is represented by this line connecting the rear and front tires. The world east and north axes are also shown here. The vehicle is controlled by rear tire force and steering angle inputs, where the steering angle controls the turn of the front wheel. The state that we are interested in estimating is position in ECF relative to a base station, not shown here, as well as the body velocity in the lateral and longitudinal directions along the car. The simplifying assumptions we make are that the yaw rate and yaw angle are known. We make these assumptions because we are concerned only with the uncertainty associated with the double difference pseudo-range measurements and not the IMU measurements. Now I will define the double difference linearized pseudo-range equation and also describe at a high level the idea of how to compute the consistent state set, which is the purple object shown here. The linearized double difference pseudo-range equation is defined here. Psi is the matrix of double difference measurements. G is the geometry matrix of line-of-sight vectors. And in blue is the position state that we are interested in estimating, the relative position between the base station and vehicle. Epsilon is the measurement noise, which we assume is bounded. We define the consistent state set as the set of states that is consistent with all measurements and the bounded measurement noise. Then how we assimilate these measurements with the state obtained through drift dynamics is by intersection between the consistent state set and the propagated set. In practice, the consistent state set is over-approximated by an intersection of state strips, where each state strip is created by finding the set of states that are consistent with one measurement. This is shown for a toy example here with two measurements. The approximation of the consistent state set is then shown by the intersection area highlighted here. Now I will discuss our validation with simulation and real-world experiments. First, I will give an overview of what the simulation and real-world validations aim to address. Then I will dive into more detail for each of the two cases. Given that drifting is an example of extreme dynamics, we start with validation and simulation. Simulation allows us to validate the zonotopic estimation framework with different noise profiles, and we can compare the framework against multiple rollouts of a particle filter. Then we validate in a post-processing manner with the real-world collected drifting data as a first step to bridging the simulation to real gap. The simulation setup is as follows. We simulated a 30-second drift trajectory as shown in the video to the right. Then we simulated double difference pseudo-range measurements using a fixed satellite assumption. We added noise to the pseudo-range measurements from varying distributions and varying distribution parameters. The 4 distributions we investigated are Gaussian, uniform, student T, and a biased Gaussian. We varied the distribution parameters to vary the amplitude of the noise added. For example, for Gaussian distribution, we varied the standard deviation from 1 meter to 10 meters of added noise. We applied the Zonotopic estimation framework through Cora in MATLAB. Cora is an open source toolbox that is commonly used for reachability-based methods. Here are a few select results from our sensitivity testing. For the full results, please refer to the paper. Here I'm showing results from adding Gaussian noise with a standard deviation of 3 meters to the double difference pseudo-range measurements. To the left is the x and y coordinates plotted in a 2D plane. And to the right are the x and y coordinates plotted over time separately. We found that all trajectories estimated from the particle filter remain bounded inside the state zonotopes across time. These are results from adding noise from a uniform distribution with bounds of plus or minus 3 meters. To the left is again the xy plane, and to the right are the xy coordinates plotted separately across time. For non-Gaussian noise profiles, we found that the estimated trajectories also remain bounded across time inside the state zonotopes. Our real-world validation with the drifting data is currently in progress. Now I will conclude the presentation. In this work, we designed a framework using reachability analysis to bound estimation uncertainty for drifting scenarios. We verified the framework with simulation rollouts and different noise profiles through sensitivity testing, and we're progressing towards the integration of nonlinear drift dynamics and validation with the real-world drifting dataset. Thank you, and we would like to acknowledge the Stanford Dynamic Design Lab as well as the Toyota Research Institute.